So, dear participant, good evening. So, welcome you, Manjunath sir. Heartily welcome you, sir Manjunath sir.
Hello, sir.
Good evening, sir.
Hello, sir. Sir, am I audible?
Yes, sir. Yes, sir. Audible, sir. So, good evening,
Hello.
sir. Heartily welcome you, sir.
Sir, am I audible?
Yes, sir. Yes, sir. Yes, sir. Yes. Audible, sir. Audible.
Okay. Yeah.
We will
Thank you, sir.
start the session, sir. Manojna. So, I would like to request Manojna, please introduce the speaker.
Yes, sir. Dr. Manjunath S. is currently working as a chief engineer at Samsung Electromechanics, Bengaluru. Prior to this, he has worked as an assistant professor at Central University of Kerala, Kasaragod, and GSS College of Arts, Commerce and Science College, Mysore. He obtained his PhD from Department of Computer Science, University of Mysore. His topic of research during his doctoral degree was video archival and retrieval system. His area of research includes computer vision, machine learning, and deep learning. He has published few research articles in international and national level journals and conferences.
Hello, Manojna.
Yes, sir. Hello. Hello. Are you able to hear me?
Yes, yes, yes.
Yes, sir. I'm done.
Okay. Over biodata.
Yes, sir.
Okay. Thank you, Manojna.
Thank you, sir.
Sir Manjunath sir, so I have given the co-host. Please share your PPT, sir.
Oh, okay. Okay, sir. So, good evening, all. Sir, I think it's echoing. So, is it clear to others?
Yes, sir. Clear, sir. Clear.
Okay. Just 1 minute, sir. So, good evening, all. First of all, I would like to thank you for.
Sir, small interruption, sir. Small interruption. So you are login in both, sir, mobile and desktop. So you mute, sir. That one.
No, sir. I have not.
So
okay.
You are getting the double sound, sir.
So now it is clear, sir?
It's, no, sir. It's doubling, sir.
Okay,
doubling,
just
sir.
I will log out and log in once again.
Yeah, okay, sir. Okay, sir.
Sir? Sir, you're able to hear me now?
Yes, sir. Okay, sir. Now,
okay, I think it opened twice. That's why I will share my screen.
Yes, sir. Please share, sir.
So now you are able to see my screen, sir?
Sir, yes, sir.
Okay, okay, yeah. So good evening, all. Sorry for the inconvenience. So as per plan, like when I had a discussion, like I thought that I will go through something related to deep learning in agriculture. So for that, I read some research articles. Basically, I am into developing applications or solutions in our company using machine learning and deep learning. So, but I, frankly speaking, I don't work on agricultural related. However, the problem domain may be different, but data will be same. So I thought that I will try give my best in presenting this one. So for that one, I tried several papers. In that, one of the papers which was very good for reading was this one, like deep learning in agriculture. So I have taken this paper and I have tried to analyze it, and based on that, I have prepared the presentation. So what I have planned is first I want to give an introduction to ML and DL and understanding of convolution neural networks. Okay, and finally comparison of different CNN network architectures. And this is about the theoretical. And in the last session, I want to show you the implementation of rice leaf disease classification. So this I have taken the data set which was presented in that research article they have mentioned. So I downloaded it. It was in Kaggle. I downloaded that one, and I have implemented using the standard convolution neural network architecture. So before starting, what I want information from you people is like whether I should touch upon the basics of ML and DL and convolution neural network, or should I understand that, okay, you people have a good understanding of machine learning and deep learning, how it works, what are the components of machine learning and deep learning. If all those things are clear, directly I can means I can skip a certain set and go. So just I wanted to know from the participants whether I should take about some 10 to 15 minutes to cover first 2 points, or should I directly go to the third point, comparison of different CNN architectures and all those things. So just I want feedback from you people. Yeah, anyone, like you can unmute your mic and tell, just to understand, like how should we plan for the session. Okay, or if any okay, I think no messages also there. Okay, then I will go ahead with my plan. If you have any queries or anything, you can raise at any time. Okay. So before starting this one, like an introduction to machine learning or something, as you all know that these machine learning and deep learning were created by pattern recognition, right? So the main area for all these things is a pattern recognition. So just to have a clear understanding, today most of the topics or almost all topics I am going to discuss about a subtopic in machine learning or pattern recognition called as classification. So I am going to explain you what is that mathematically what it is. So let us consider this one. In this, so whatever we have on the right side, it is called as a pattern space. Pattern space means it's about like which contains all the patterns which we need to learn. Means in any machine learning or deep learning projects, right? So we are trying to solve some problem. Let us say we need to recognize a simple thing like a recognition of handwritten numerals. Okay, in that case, if I take handwritten numerals, let us take handwritten English numerals only. So this pattern space becomes a space where all the handwritten English numerals will be present. So here I have shown only 4 classes. If you see for pattern for handwritten numeral recognition, we will be having 0 to 9. So if I take one class, so we call it as a class O1. So it will be containing all the samples related to class 1. Same way, all the samples belonging to class 2 will be in O2 and so on. So that is what we call it as a pattern space, or it is a complete population which has been used for the training. So, or we can also say that it's just like our training set. Means if I want to develop any application in machine learning, we need to use a training set. So for that, we create that one. So whatever we have the data for training, that will be called as pattern space. Okay, and on the left side we have an instances space. So when I say instance space, in the instance space we will be having a set of samples which we don't know whether it belongs to class 0, class 1, class 2 or class 9. Okay, so just we have the data. I need to understand if I give a sample like O1 to which class it belongs, whether it belongs to class 1 or class 2 and so on. So all these machine learning or deep learning algorithms, what they are going to do is they are going to develop a mapping functions which take the input, this O1, O2, O3, ON, and produces an output saying that to which class does it belongs. Means if I take this O1, the O1 becomes X for me, and this machine learning, it's a simple function, it will be generated. So that function, it takes a data in the instances space and map it to a pattern space called as Y. So you take any algorithm in machine learning, especially in classification, so it will be trying to find out a mapping from an instances space to the pattern space. So this learning or deep learning algorithms are nothing but this function F. So example, if I try to give a function, a problem to any one of you to find a solution, like a very simple thing like searching algorithm. So we can come out with multiple functions, right? Same way in machine learning and deep learning, we have multiple algorithms. So in today's session, we are going to study about these functions. What are the functions we have in machine learning and deep learning? That will be very quick. We will just wrap up very quickly related to the introduction, and then we move on to the deep learning architectures. Okay, so you people may be like, most of you may be working related to machine learning. You know that if I want to create any project, these are the basic steps we use. Means from the problem domain we take the data, right? We understand the problem domain, and with respect to that problem domain we collect the data, and we will try to analyze data, and based on that we are going to do some feature engineering, because raw data cannot be understood by the computers. So the data has to be converted into our machine learning algorithm understandable format. So for that we extract the features. We call it as feature extraction, feature engineering, and so on. Once the features are extracted, we choose appropriate model, that function F. So we have plenty of functions F. So we need to identify which function need to be used, and we need to train that one. So once it is trained, we are going to evaluate and we will build an application. That's all. It's a very simple approach. So that is what a basic introduction to machine learning. You take any machine learning with respect to supervised learning. So these are the steps involved. If I want to develop a such system, right, I said that we need to have a train and evaluation. So as I said in the beginning, we are going to create two sets. One is pattern space, another one is the instances space. So these two things, first two things, training set and validation set, can be called as an instances space, which will be used for learning the machine learning algorithms. So I will be using algorithms sometimes, and parallelly I may use models also. Algorithm and models are one and the same. Okay, so in order to develop the machine learning models, we need to have two sets. One is pattern space, another one is instances space. So using the pattern space, we are going to train the system. We are going to come out with the function F. So once the function is ready, I need to test how it works on an unseen data set. So that is what the testing set. So using the testing set, we will try to understand the performance of the system. So if it is meeting my expectation, we call it as KPI, key performance indicator. Like I may say that the accuracy should be greater than 95%. So that is what my KPI. So on the testing set, the function, whatever I have learned, or the model which I have learned, if it is meeting my KPI, I will try to deploy it in the real field. Okay. So that's what for a data, if you want to train any machine learning, we need to have three sets. That's all. So these are the different methods to generate that data set, like bootstrapping, word out, and cross validation. Assuming that you all know these things, I will just skip it. So very important thing what I need to tell you all. So what these machine learning algorithms will do. So we will take machine learning algorithms, right? We will say that, okay, I trained the data and I got the model. So actually what this model contains, that we need to understand. This is very important when we want to move on to deep learning. See, in case of machine learning, what happens, as I explained in the beginning, we are going to take the data, raw data. From the raw data, we are going to extract the features. So once we extract the features, so the data will be transformed into from original space to feature space. Means if I take let us assume that I want to classify the participants into male and female classes. So I may take height and weight as a feature. So individually, we are, or physically, we have samples, right? So once I extract the height and weight of each sample who have participated in this seminar, right? So V becomes a point in a two-dimensional space where one axis is height, another axis is a weight. So individually, V becomes a point in the feature space. That's all. You take any machine learning algorithm, the visualization will be like this. You take any data, once you extract the features and represent it, it will be a point in a feature space. Example, somewhere here we have taken two features like a length and lightness. Okay, so here each point is a sample. Okay, so we have two types of points, green and red. Okay, so what this function will be doing means this model will be trying to do, if it is a classification, it will try to find out the region for individual classes in the feature space, like how the samples are distributed and in which region each classes will be falling in. That's what we are going to understand. So that is what the feature space you're looking. So there are two regions. One is green region and the one is the red region. So in that we can identify. So all machine learning algorithms will be trying to find out these decision boundaries. Especially I'm speaking with respect to classification problem. We call it as a decision boundary. So this decision boundary can be either linear or it can be non-linear. When I say linear, the decision boundary will try to separate class 1 from class 2 using a straight line. Okay, if it is not possible, it will try to find out the decision boundary using a curve. So that is called as a non-linear boundary. So it can be anything. So what I want to convey you people here is, you take any machine learning or deep learning algorithm, the purpose is to take the data, extract the features, and represent those data in a feature space and try to find out the regions in which the classes will be lying in the feature space, and how can I separate it, so that in future if I get a test sample and if I just put it on this feature space where it lies, that I need to understand. Based on that, I can say that, okay, the sample belongs to region 1 or region 2. So we call it as region 1 and region 2. In general sense, we call it as a class 1 and class 2. Example, if I take so let us assume that just simply this is what the trained model. So when we say that a model has been trained or a machine learning algorithm has been trained, it will just take the samples and it will create the feature space and it will identify. Now if a test sample comes, let us assume that this is a test sample. So if I extract the same feature for this, probably it will be having x1 and this will be having x2. Right? So if I take this and if I plot, if that sample falls in this region, then I will call it as, okay, this sample belongs to red region. So it is a red class. So it's a red dot. If I take this and if I plot it into the feature space, and if that falls in this region, then I will call it as, okay, the sample which was given as a data to test, it belongs to green region. So it's a green dot. So like that way we are going to do that. That's all. In any machine learning algorithm, we are going to do this one. So any doubts in this? This is an example of a non-linear boundary. So assuming that you understood this one, I will move on. So one of the challenges in this decision, sorry, one of the challenges in this decision boundary identification is like is how good that decision boundary is, whether the decision boundary as identified or created properly or not. See what happens whenever we are generating the decision boundaries, right? If the decision boundaries are not created proper, there will be a issue during the inference. Inference means testing. So what happens? Let us take a simple example. So these decision boundaries are the knowledge what we give during our internals to the students. Means during the class we train them and we will try to assess them in the internals, right? So based on that we can assume that the decision boundary whatever we get during the training phase, it will be a proper, means they have learned the syllabus or the course whatever we have explained is proper. Okay, and in the real exam, in the final exam, if we give a question, if he is able to answer that one properly, means he has learned properly the syllabus. Now the question comes, let us assume that what I will do in the exam, the same question which was given in the internals, okay, if the same question was given to him and if he has learned that one, definitely he will be able to achieve 100% accuracy, means 100 marks, right? On the other way, if I give some question which has to be answered based on the knowledge what he has learned during the classes, right? If he is not able to answer the question, such questions, then I will say that he has not learned properly. So if I take the first and second case, which whatever I have explained it, right? So if the student is able to answer the question which was well prepared, and if he is not able to answer the question which has to be answered based on the inference, then I will say that he is underfitted. Okay, means yes, sorry, we call it as a overfitted. Means overfitted means he has learned only the things which a teacher has taught in the class, but he will be not able to answer the new things. So that is the one thing. That is called as a overfitting. Means our decision boundary, the same thing happens in the machine learning algorithms also. Means if I take a data and if I learn the model, means if I train the model and if the decision boundary works like this, so it says that okay, this belongs to region 1, so this is region 1, and the next belongs to region 2. Okay, so this is what it has understood during the training. What I will do, I will give the same samples whatever we have used for training, right? I will give the same samples as a testing samples. If the algorithm was not able to correctly classify even the trained samples, then I will say that the algorithm has not learned properly even the training data set. So that is called as an underfit. So we should be very clear whenever we are developing an algorithm, whether my machine learning algorithm or deep learning algorithm as overfitted or underfitted, that should be very clear. So why I explained this one is, in deep learning, while training, we have a mechanism which will be used during the training. We call it as epochs. I will explain those concepts. That time we are going to check what is the validation accuracy and all those things. That's why I explained you people. I hope like this you have understood. See, if the student was able to answer the question based on his experience or based on the inference, then we say that he has a good generalization knowledge, or he has a good knowledge about the topic. Same way, even in the machine learning, if the decision boundary has been formed properly, and on the unseen data, if it is able to recognize most of the unseen data, we say that the model is generalized properly, or else we will say that the model is poorly generalized. So generalization is a very important topic in any machine learning or deep learning. So I hope you understood what is difference between generalized model and non-generalized model. Okay, that is what the poor generalization. I will skip this one. So this is what about simple introduction about generalization or decision boundary. As we are discussing about the classification, just I will give a simple example or understanding of what classification is. So in machine learning, we have different kinds of learning. Basically, one is supervised learning, and the one is unsupervised learning. So supervised learning, it is called as a classification. Unsupervised learning, it is called as clustering. So in case of classification, or in we use models or classifiers. So those classifiers, what it will do, as I said, if from the raw data, the features will be extracted. So those features will be given to the classifier. Classifier already it has trained on the trained data, and based on the decision boundary, it will say whatever the data you have given, it falls in that particular region, and each region will be having a class label, and that will be the output. Means if I am trying to classify the participants as male and female based on the weight and height, right? So height and weight will be the features, and we will be the samples. And if a new sample has been given, some, like let us say weight is 50 kg and height is some 6.2 feet or something, then the class label will be either it says that okay, the sample is male or sample is female. So I hope you understood what is classifier. Entire thing in today's discussion, we are going to discuss on these things. Okay, so this is what the classification. Just for sake of completion, you know that different classifiers are there. That is a k nearest neighbor classifier, which works based on the majority voting technique. It is also the same thing. So it will try to identify, given a sample, to which class it belongs. Okay. Another classifier, we have a support vector machine. So this is another type of function. So we can call nearest neighbor as a one type of function, support vector machine as another type of function, but the way they implement is different. So in case of support vector machine, based on the support vectors, they will try to identify the regions. So they will try to find out. So based on this, they will say, okay, this is a class or a region 1, and this is a region 2, and they will try to give the results. So that's all. So these are the simple examples of classifiers. Like this way, we have plenty of classifiers. Probably you people can go and read if you don't know about what are the different classifiers here you have, or the underlying structure is the same. All the classifiers, they want to identify the regions. So, and for each region there will be one label. We call it as class 1, class 2, and class 3, like that way. So this is another region, we can call it as a class 2, those things. So those things are called as like a classical machine learning algorithms. Apart from that, we have another type of classifier or learning algorithms called as neural networks. So I will try to touch these things in a very quick manner. So as you all know that today's the entire research community, especially machine learning, is behind this neural network. So it was not started now. It was like around 30 years back itself, we had neural networks. But that time, it was not so much famous or not used. One of the reason was a computing facility. So this neural network requires a huge amount of processors and data. That time we could not have such things. That's why that was not into the limelight. So with the advancement in the infrastructure of our computer facilities, neural network once again came back into the picture. So we are going to understand. And this neural network, it is same as our human brain, like our neural system. So they will try to create a artificial neural networks. So I will skip all these things. Okay. Just I want to explain to you how these biological neuron and artificial neurons are there. Okay. So as you all know that our brain contains millions of neurons, and these neurons, we can just assume that these are like a circuit of bulbs. Okay. So like in our brains, you are in general, you can visualize that there are plenty of bulbs which are connected. Means each one is connected in a different way. Okay, so these connections are called are responsible in learning. Means let us assume that this is our brain. Okay, so if I say this is our brain, if I am good, if a person is very good in cooking, let us assume, probably certain part of the circuit will be activated. Okay, means he has been trained, or he or she has been trained in cooking for a long time, and because of that certain part of the brain has been activated. If someone is very good in mathematics, means so for that there is a certain circuit in our brain, okay, which some set of neurons are very much important for learning the mathematics or solving the problem in mathematics. So that part of circuit will be very strong. Means just assume that these are the bulbs. If this is for mathematics, all these bulbs will be glowing with a high intensity. If this is for cooking, so these set of circuits will be working fine. So how these circuits will be done, or how it will be intensive in the signal, means because see, if someone says that he is very good in mathematics, not like it's you might not have learned mathematics in one day, right? So he will be get trained in mathematics from the childhood. He might have generated interested in solving the problems using mathematics. So he may be very much interested in understanding different concepts of mathematics. He might have got good hands-on experience related to mathematics. So if you do that thing repetitively, what happens? That part of the circuit becomes very strong. Means the neurons will be very activated, these links will be very activated. So he may not be interested in the cooking. In that case, what happens? These circuits will not be very much active. Okay, so that's what I told you. So please keep in mind, so repetitive training, so this is very much important for us. If you want to be good in something, what we need to do? Repetitively we have to learn and unlearn it. So continuously we should be learning that one. We have to forget and we have to relearn that one. So if you do that one, what happens? So we will be very good in that subject, or in that sports or cooking or whatever, arts or something. So the same thing has been used in the artificial neural networks also. Means if I want to solve any problem, we create one architecture. So this is a simple architecture. Okay, so we can create one architecture using neural network. So based on that, like how we train the human brain, right, we can train that neural network to perform some task. So now it is a task dependent. Like someone may be very much interested, or someone may be doing a research related to character recognition of their mother tongue. If someone is working on character recognition for Telugu, right? So they will be creating a neural network and collect the Telugu characters, and they will train it. If someone is working on Kannada characters, so they will collect the characters and they will do it. Or someone may be working on the face recognition for an industry where they have some 1,000 images, 1,000 employees. So they will try to collect 1,000 employees images, and they will try to train the system. So when I try to train the system, like as we explained, even this neural network, it will be trained in such a way that with respect to each class, it will be very active. Means it will try to learn the task. So in machine learning, when it comes to neural network, basically we will be having three important things. So neural network is made up of three important things. One is called as input layer. The first one, the leftmost in the diagram, it is called as the input layer, okay, which is responsible for feeding the data to the network. And the last layer, it is called as an output layer, which is responsible for generating the classes. Means if I am working on recognition of zeros and ones, only two class, binary class, so I will be having two nodes. Or if I am working on numeral recognition, handwritten numeral recognition, right? So we English numeral recognition, we will be having 9 outputs. So because given a sample, it can be either 0, 1, 2, 3, so on 9, right? So we will be having 9 outputs. So that is called as a output layer. So you should be very clear, like the number of nodes in the input layer will be equal to number of features in your data set. As I said in the beginning, this machine learning can't learn the data directly. So we want to convert that one into some format which that algorithm understand. So for that we do feature extraction and all those things. So if I have extracted 3 features like length, height, and width, so the number of nodes in the input layer will be 3, and number of nodes in the output layer will be 10, depending upon the classes. The between one is called as a hidden layer. So this hidden layer, that is what the architectural design. So that is the role of the machine learning engineer or deep learning engineer, where he is going to tell how many such layers should be present between the input and output. So if I have if I am an neural architect, so I will say, okay, depending upon seeing this data set and visualizing that data set after doing EDA, I will say, okay, this requires 3 hidden layers, and let us say in the first hidden layer I will be having 10 nodes. In the second hidden layer I will be having 40 nodes. In the third hidden layer I will be having 100 nodes. So like that way we are going to decide that one, and how it should be connected, everything is the architecture. So once we get that one, so we will just feed the data, it will try to learn that one, and it will try to produce the output. So probably like I am assuming that most of you know these neural networks and all those things. I'm just moving on so that we can discuss on the topic of use. So how this training will be done, just for sake of completion. So when you give a data, this training will be done based on a simple mechanism called as sum of product of the input variable and the weight. So as we understood this, see, this data will be giving x1, x2, x3. Means if I take a sample S1, it will be having 3 features. Let us say F1, F2, F3, or x1, x2, x3. So I have x1, x2, x3, and I have a node in this hidden layer. So I need to establish a connection between these two. So if I want to establish a connection, means there should be an edge going from this input node to this hidden layer node, right? So whenever there is an edge, for that edge, there will be one weight will be associated. So if there are 3, and if I have here 3 into 3, 9 weights will be there. So based on those number of weights, we are going to perform an operation of W1 into X1. Means very simple example, if I take this one, if there is only one node and if there are 3 features, X1, X2, X3, so these 3 input nodes will be connected to this node, means there will be 3 edges. So for each 3 edge, we will be having W1, W2 and W3. So how this neural network works, it will just multiply x1 into w1 summation plus x2 w2 plus x3 w3. So that will give an value. That's what we have given here. So for each node, there will be one threshold value. This is the simplest one. So if the value whatever we have generated based on the summation of product of this input and weights, so if it is less than threshold, we will say 0, or else we will say it as 1. So what are these zeros and ones? So I told that like in human brains or in neural networks, we need to establish a circuit. We need to generate a circuit, right? So if I have multiple nodes here, right? So let us say if I have like this, very simple example, right? So let us take, this is the input node. So this is the connection we have now here, right? So if this part has to be activated to send the data for the next node, so what I need to do, I need to take the x1, x2, x3, multiply with weights, and something will come. So now the algorithm has to be trained. So when I say the algorithm has to be trained, means it has to get the appropriate weights and this x values and make this node as a active node. So whether this node should be active or it should be inactive, that we have to decide. So this function will decide whether this node should be active or inactive. When I say active, so this node will try to send the signal to the next node if it is active. If it is inactive, it will not try to send the signal to the next node. So if you see here, so we will do some operation here, and based on that we will get some value. So if that value is less than the threshold, we will say that okay, don't send a signal to the next connected node. So let the weight of this one means let this not play any major role in learning the data. Okay, or if this has to be very activated, then it will generate a very good high impulse. Means example, if this one is greater than the threshold, then it will be 1. 1 means it will try to send more signal to the next signal, next node. Like this way, a circuit will be built during the training of the neural network. The same thing happens in our brain also. So if you keep on training, so certain part of the brain will be get activated. Means certain part of the circuit present in the brain will be get activated based on these values. So same thing will be done in the machine learning algorithm also. So now let us try to correlate between two things. In the beginning of the session, I told about any neural network, it will be responsible in generating the regions or decision boundary. Like it says that, okay, this is R1 and this should be R2, correct? So this is what any classifier has to do. So what this learning is doing, how these things are related, that is what we need to understand. See, these decision boundaries are obtained based on the weights. So we said that each edge is associated with the weight, right? So these weights W1, W2 or W3, whatever we have, right? So these weights, initially it will be based on the random values. Random values will be generated and we will take X1, X2, X3, we multiply with the weight W1, W2 and it generates some output. Okay, so whenever it generates the output, we will try to see how much error we have. Okay, so because it's a random, normally in the initial training, the errors will be more. So once we get those errors will be feedback to this algorithm or to this neural network. It says that, okay, see, algorithm, so you are doing the mistakes. So I expected to get a 0, but you are outputting or you are predicting it as 1. So this is what wrong. So you try to adjust your decision boundary. So when it says that adjust your decision boundary, it will not try to design this decision boundary. It will try to adjust this weight. See, in the entire machine learning algorithm, what we are trying to do, it's a very simple multiplication of weight and x, right? So these are responsible in identifying the decision boundary. So we will try to see this one. So if you have understood correctly, when I say that I am training the neural network means, what I am trying is, I am trying to find out the appropriate weight values, W1, W2, W3. So this appropriate weight values will be done based on the errors, whatever it has obtained. We will try to give that, okay, this much of error you are generating, try to learn properly. Then it will try to adjust this weights. Okay. So that is the one of the important thing we need to understand, because these things are very important when I start explaining you about deep learning. Okay, DL. So I hope like this is clear to you. And how we are going to train? Let us say I have 1,000 samples. Let us assume that I have 1,000 samples and I am working on a 10 class problem. Okay, means from each class I have 100 samples. So how this neural network will be trained? I used one a word called as epoch, E-P-O-C-H. What is this epoch? Okay, so what we are going to do is, we take these 1,000 samples and we will give that one to this neural network. So all the samples will be given to this neural network so that it will try to learn. So if we give all the training samples, whatever we had for training, this 1,000 for training at once, it is called as epoch 1. So it will try to see entire data set one time, then we will say it is epoch 1. So based on that, it will calculate some errors and it will try to find out what is the accuracy, and based on that, the feedback will be sent to the neural network. It will try to adjust its weights. Okay, then same set of 1,000 samples once again will be given to that neural network. So you are getting that one, right? So first time we gave the first 1000, means all 1000 samples whatever we had, that to the neural network. The neural network understood and it tried to predict. Because it was the initial training, it could not produce the good results. So there were some errors, and it will try to adjust the weights. So second time we will take the same 1000 samples. Once again we will try to give it. It will try to learn, and that time the probably the error may be getting reduced, and it will try to update. So like this way, it will try to find out for certain number of epochs. Let us say n epochs, like 10 epochs, 20 epochs. So if I say 10 epochs means the same 1000 samples has been given 10 times to the neural network to learn and understand. So during that training, what happens? The weights will be getting adjusted. As the weights are getting adjusted, the decision boundaries will be getting adjusted properly. That's what we are going to do. So this is what the simple example will do. Very important thing in the neural network we should know is the activation function. So I said that. So the nodes are responsible to make it activate, whether I need to send a signal or not. So it is just a simple function. Those functions are called as activation functions or as squash functions. So in the literature, we have different activation functions. Okay. So normally we use sigmoidal activation function, tanh hyperbolic function. So we have ReLU activation function, leaky ReLU. Many activation functions are there. So that you can try to learn by yourself. Let us see a very simple example. Let us say this is what my data set is. So now I have the entire raw data has been converted into the features. So any supervised learning, we will be having the data. These are called as features, and we will be having the labels. These are also called as class. So it's a two-class problem. So what we will do, we will take this data one sample at a time, and that will be given to the system. So if I give this one, what is the expectation from my output? So this is the output node, right? So what I expect is it should produce it as a 0. So when I give this one, initially I will be having weights here, W1, W2, W3, and so on, which are generated randomly. And based on that, using the sum of products, right? So it says that it is 0.8. So my expectation was 0, but it gave me 0.8. So there is an error of 0.8, right? So this will be sent back. Okay, see boss, I gave this one. My expectation was 0, but you are trying to predict 0.8. So it's wrong. You try to update yourself. So when I say update yourself, it will try to adjust the weights. That's all. It will try to do the weight updations. Like this way, next another sample will be given. My expectation is 1, but it predicted 0.9. Okay, the error is very much less. 0.1 is the error. So once again, it will be feedback. It will try to adjust. So like this way, if we start giving the data continuously for n number of epochs, it will try to adjust the weights, and finally appropriate weights will be identified, and that will be responsible for generating the decision boundary. So how the decision boundary works like this. So based on the initial weights, this may be the decision boundary. Okay. So if we keep on training and updating the weights, the decision boundary will be trying to adjust. So now you can see that this is the actual decision boundary. It has been updated. So that is the responsibility of the training of a neural network. So that is what, and the accuracy of these neural networks depend on these things, like training set, how many samples you have, how good features you have extracted, and how the network structure or architecture you have designed. That's what. So this is what I will skip these things, because assuming that you people know all these things. So features you can extract, there are multiple algorithms. So that is what choosing the features is the most challenging thing in any machine learning algorithms. So that comes by experience. So why I explained all these things is, see, for any classical machine learning, if you are working on a classical machine learning algorithm, most of our time depends on two things. Like we will try to spend on, or like which feature is the best feature. So if you are working on a data set, where already someone has extracted the features, you may not feel that much challenge, because someone already has done your job. If you are working on a raw data, what happens? You need to extract the features. So that feature extraction itself is a big area. So depending upon your data type, like whether it is a signal, image, or a text, or a video, you need to extract the features. And if you take individual features, example, image. So image, from the image, we can extract like a color, texture, shape features, and so on. So if I take the color, in color itself, we have hundreds of feature extraction technique. If you take shape, we have hundreds of feature extraction techniques. So which one should be used is the most challenging.
Sir, Manjunath sir.
Yes.
Small interruption, sir. Please give the 10 minutes breaks are 7:50 to 8 o'clock.
Yes, sir.
Then you start.
Just I will complete this one and I will give a break.
After that, I give 10 minutes, sir. Okay, no, sir?
Yes, sir.
Okay, thank
you. Okay. So that is the one of the challenging. And another one is this learning algorithm. Already we saw that neural network, support vector machine, k nearest neighbor algorithms. Many algorithms are there, right? So which one should be used is the most challenging things. So like the question comes, why I should be bothered about extracting these features, or which algorithm to be used? So to solve that one, so people understood, okay, coming to the current scenario, the best algorithm for learning is a neural network. Let us use the neural network. How about solving this problem? Like which features should be extracted? So how human brain works? So when they did lot of experiments and all those things, they understood that the human brain tried to recognize many things. Like we are able to recognize thousands of people's, right? And we are able to recognize thousands of objects or whatever it may be, right? Because our brain stores the data in the form of an abstract, not in the form of what these classical will work. So for that, they understood we should think about a hierarchical level of features from low level to the high level. So based on that, they will try to understand, and they understood, and they came out, okay, we should extract the features in a hierarchical way. Example, if I take this face, you can see that initially it will be the raw data, means primitive shapes like edges and all those things. From those, they will try to find out the components. From components, they will try to build the models. So if you see all these things, it will be like this. So can I extract these things automatically? That was the question. So that's what the feature of machine learning and deep learning comes. So machine learning, in case of machine learning, mainly they spend time on extracting the features and coming out with the algorithm. So in order to solve this problem, they started using, like, they combined these two things, feature extraction and classification. So they used feature extraction and classification in one thing called as deep learning. So using the neural network, just you feed the data, automatically it will identify the features which are responsible for learning purpose, and also they learn and they do their task. So that is what the deep learning comes into the picture. So now it is 7:52. We will take a break for 10 minutes. We will come back by 8 o'clock. So any doubts, you can ping me, or if you want change in the presentation also, I will try to change it. Sir, shall we start?
Okay, sir, start the session, sir. Okay. Sir.
Yeah. So some of the one of the participant has mentioned in the beginning. I could not notice that one. They wanted comparison and CNN models and implementation. So directly, shall I start that one, sir? Assuming that participants know
Yes,
about
sir. Yes,
convolution neural network.
yes, sir. Yes, sir. No problem, sir.
Yeah. Anytime if I'm explaining the basics, if you want to skip, let me know so that it will be benefited to most of the audience. Yeah.
Okay, sir.
So assuming that you people know about convolution neural network architectures, just 1 minute. So now audio is clear, sir? Am I audible, sir? Hello.
Yes, sir.
Okay. So assuming that the audience know about convolution neural network, so probably the basic components of any convolution neural network consist of a convolution, right? So I am just taking the names of the convolutions. The first thing is about this convolution will be done, and another thing which we are going to use in convolution neural network called as a pooling. So to reduce the size of the response images, and also activation function we discussed, like these are the functions which are responsible to activate the neurons or not. So to what level it has to be activated, everything will be decided with these activation functions. So basically these are the three building blocks of convolution neural network. Apart from that, we will be having one more neural network which is responsible for classification. Means, so whatever we have in these three things are responsible for extracting the suitable features from the images, and once we extract the features, that will be vectorized and given to the neural network. So in this entire thing, the last layer in the neural network, normally the last layer will be either a sigmoidal function or it may be a softmax. So most of the time, if it is a multi-class problem, we are going to use the softmax function. So I hope like you know all these things. So now coming to this one, if I want to explain you all about different architectures present in the literature for a convolution neural network, right? So I am going to use certain notations. The notation is like if I say convolution 3 by 3 means it's a convolution layer and the size of the mask is 3 by 3. So if I say average pull 2 by 2, 2 by 2 matrix will be taken on the response image and averaging will be done, or max means we'll be doing the max pulling. So concatenation means if I want to concatenate multiple layers output, so we are going to use this one. So this corresponds to a dense layer or a fully connected layer. So activation functions will be represented like this. So a circle with yellow color and T means it's a tan hyperbolic, or R means a ReLU hyperbolic. So batch normalization, it's a one type of normalization which will be used for batch processing. So in case of epochs, like I mentioned about epochs, right? So if I have 1,000 images, all 1,000 images cannot be used for learning because it cannot be held in the memory. In that case, we need to process batch wise. So we use a technique called as batch normalization. It is the same as our normalization technique. We use data normalization or data standardization in machine learning, right? The same concept will be used to normalize the data in batches. Okay. So mainly in any convolution neural network, if we are trying to understand different convolution architectures, the difference between the initial versions of convolution neural network and recent convolution neural network is how they are going to stack the blocks of these convolutions. Means if I take this one module A, right? So if it is written like this, it says that there will be a convolution 3 by 3 followed by average pooling. So this will be one module. So they can call it as a module A. So someone may be module B, they may call it as with a different size of the convolution, whether they use average pooling or max pooling or global average pooling and so on. So they are going to design their own blocks. Okay, that we are going to understand. So we should understand entire architecture, standard architecture, whoever have proposed, they will be giving their own modules. Okay, module A, module B, module C. This is a simple example. And one more important thing is this part. So if someone says that module B into 2 means, so module B, like if I take this one module B into 2 means, so this thing will be copied 2 times, or it will be stacked 2 times. If it is here n, or if it is 10 times means, this block will be stacked, means it will be concatenated this way. So with this building blocks, let us try to understand from the basic architectures to the standard architectures. The first neural network, convolution neural network, was proposed in 1998 by Lee Kuhn. So he's also called as father of deep learning, because this was the first paper which used a convolution neural network. So this was used to recognize the handwritten numerals. That one. So the input size of the image was 32 by 32. So in the convolution process, they first used a convolution with a convolution filter of 5 by 5, followed by average pooling. Here we have written T, right? Means they use a tan hyperbolic function. So they used convolution, average pooling, convolution, average pooling. In both the convolution, they used 5 cross 5 filters to the convol, and tan hyperbolic used. So this will be the final output, means of the feature extraction. Whatever we have average pooling 2 by 2. So whatever the responses we will get, that will be concatenated and it will be formed one vector. So that forms around 120. So then the neural network of 120 neurons will be created. In the next hidden layer, it was 84, because they worked on handwritten numeral classification. So it added 10 class. That's why we have 10 in the output. So this is the final output layer of the neural network. So it had a 10 neuron and they used a softmax. So this was the first paper used for convolution neural network. So what is the beauty of this paper is, what we need to understand, till then we were using only one layer or two layer, but they tried to stack two different convolutions for feature extraction. So this is what the feature extraction part, okay, and this is what our classifier. So this is classifier and this is a feature extraction. So just you need to input the data and this entire process will be combined to obtain the feature as well as to do the classification. Now, if you see, try to understand what the learning process will be done. What are the things it will be learning? See here, if I take the first part, already we discussed in the beginning, right? So in the first part, if I take this one, right, here we have 120 neurons here. Okay, so answer here in the next layer we have around 84 and it's a fully connected. Means if I take one neuron in the first layer and another neuron in the second layer, it will be connected with respect to all neurons. So it is a fully connected layer like this. So here we understood, right? There will be weight for each edges. So we will be having so many number of weights, right? So that is what the weight we need to learn. So that is a learnable parameter. Okay, so if I take like this, in the entire architecture neural network, the neural network has to learn about 60,000 parameters. So now you can imagine this is the simplest architecture we have and it has to learn 60,000. So in that case, how much of data it has to learn, and how many number of epochs we have to give, all those things is a challenging thing. So this was the first thing, and this was the simplest architecture they used. So if you just notify this one, the first paper was in 1998. The second article was in 2012. It is about more than 14, nearly 14 years. So after 14 years, why it is such a big gap? I explained in the beginning, right? So when this neural network was created initially, our computing facility was not good. That's why, like, we could not invent very quickly. So after advancement of the neural network, means the computing process, so the architecture also started growing. So in case of this previous, it was just 2 layers, right? Means 2 layers of convolution and 3 layers of fully connected layers. So in 2012, they came out with a deeper architecture. So that's why it is called as a deep learning or deep neural networks. So if you see here, so we had around first 2 convolutions, and then what is this? What is the meaning of this one? So we have one convolution block with a 3 cross 3 into 3, means it's a copy 3 times it will be copied. So totally how many convolution layers will be having? 5 convolution layers. In the first paper we had just 2 convolution layers and 3 neural networks. So here they had 5 convolutions, 3 plus 2 5 plus 3 fully connected layers. So and also they used different convolution filter sizes, like they used 5 cross 5, here they used 11 cross 11, 5 cross 5, then 3 cross 3. And also if you see the number of neurons, there it was just approximately it was 120 and 84 and 10. So here they used 4096 4096, means more number of neurons. And if you see the last layer, it is 1000. So what it indicates, so in the previous they worked on 10 classes, but AlexNet they worked on 1000 classes. That's why we have 1000 neurons. So that was the difference between the first and the second paper. Now another important thing is this point. So first paper they used around 60,000 parameters to learn, whereas the second paper, the architecture AlexNet, it was supposed to learn about 60 million parameters. Now you can imagine, like as the size of the neural network increases, the size of the number of parameters to be learned also increases. That was the major difference. Means comparing LeNet, the first paper, and AlexNet, the architectures was bigger and the more number of parameters were supposed to learn. So what was the novelty in that paper is, so even they came out with another approach for as an activation function called as rectified linear units. So they also used ReLU as an activation function. Nowadays, if you see any standard architectures, normally they use the ReLU activation function. Assuming that you know all these activation functions, I will skip. So also the novelty in that architecture or in this paper was like use of overlapping, like pooling. Like earlier AlexNet, it was just skipping that one, but they used, and also they used dropout and data augmentation. So what is this data augmentation? See, if you want to learn a very good deep learning architecture, you should have huge number of data set. So if we don't have large data set, so the algorithm will not able to learn properly, or it will be overfitted. So I explained in the beginning what is meant by overfitting, right? The same thing will occur if you have less number of data and if your architecture is very big, so it will try to overfit. Means it will just learn the data whatever you have given. It will not be able to generalize. Means it will not able to recognize the unseen samples. Okay, so they used, in order to avoid that problem, they used the top technique called as a dropout and data augmentation. That is what the difference between the first and second paper. And also the implementation wise, in case of AlexNet, they used the parallel implementation because it was very big. The size was 224 by 224. Whereas in case of the first architecture, it was just 32 by 32, a small size image. Now it is an RGB 224 by 224 into 3, and also the network architecture is very big. They have used bigger size of filters and all those things. So in order to work efficiently in 2012, they came out with the parallel architecture. That was also very good invention for deep learning. Okay, so that is about the first two architectures. So the next one is about VGGNet, which was designed in 2016. So the difference between the AlexNet and VGGNet is as follows. Like they will try to combine or they will try to improve the depth of the architecture. Means if you see here like a convolution 3x3, convolution 3x3, and max pooling. So this is one block. So if I take this one block, so into 2 means this was copied 2 times. Next, they add another block V2. So that block add convolution 3x3, convolution 3x3, convolution 3x3, followed by max pooling. And they also used a rectified linear unit RLU, which was proposed in AlexNet, and that was stacked 3 times. Means the same block was stacked 3 times. So this architecture was little bit bigger or deeper than the AlexNet, and they used the same neural network thing for classification purpose. So this is for feature extraction, and this is for classification. So even they worked on the 1000 classes. So the major difference between AlexNet and VGGNet is it was a more deeper, or it was twice deeper than the AlexNet, roughly, approximately. Now you can see very important thing is this one, like how many parameters it was supposed to learn. Okay, so when I say the parameters, the first paper used about 60,000 parameters. Second, it was around 6 million something. The third paper was about 138 million parameters. So now you are, I think you are able to appreciate like how these neural networks will try to, why this neural network take more time on training. Okay, because they have to identify these 138 million parameters. So whenever I say that these parameters are being trained means, in case of convolution neural network, these parameters are responsible for extracting the suitable features. Okay, abstract level of features, so that the data will be learnt properly, and also they are responsible in generating the appropriate weights, so that the decision boundary will be generated properly. So I hope like for all of you this one is very clear to you people. Okay, so this VGG group, actually it is a research lab where they work on such things. They didn't came out with only one type of architecture called as VGG16. So this was the architecture view of it will looks and all those things. So probably you can go through the these things. So they came out with multiple variants of VGG. So if you see here, we have multiple variants of VGG. So totally they came out with 1, 2, 3, 4, 5, 6 variants of the VGGNet. So let us try to understand. If I explained about the VGG16, right? So when I say VGG16, it has 16 layers of convolutions and fully connected layer. Let us try to count this one. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and this one is 3. Totally 13 plus 3, 16 layers are there. In those 16 layers, 13 are convolutions and 3 are fully connected layers. Okay, so if I take this one, this they call it as a 11. So we can call it as VGG 11. So VGG 11 means even if you count here, it will be about 8 layers plus 3 fully connected layers. So, and also they add a 19, means 16 convolutions and 3. So this was more deeper than the AlexNet. So that's why it had around 138 million parameters. So now we are going to see this one, how this will be implemented, those things. I will show you that demo. Already I have given the code also to you people. I have shared it. You can use that code if you are interested. So VGG 16, when we had such things, like even the accuracy was getting increased. So it's not only deeper, the accuracy was also getting increased. So till then, we had the research community had an intuition, like as the size of the or the depth of the network architecture increases, the performance also increases. But in this paper, if you read this paper carefully, they will try to identify, like, okay, it's not only that increasing, so there will be some issues also. The same thing was identified by the Inception. So this Inception is by Google. So it is called as Inception Net, or also it is also called as Google Net. So what they understood, like as you increase the depth of the neural network, it's not true that you will be increasing the performance of your system, means accuracy or something. They also identified one thing, like as the size of the or depth of the neural network increased, there was a problem of something called as vanishing gradient problem. So what is this vanishing gradient problem means? As we all know that, so we will take the input data, right? For any neural network, we will be having the input, and that will be passed through our hidden layers. So what we are trying to do, we are trying to have more number of hidden layers compared to the last layer, right? So we'll be having more. So when it has to pass through so many number of layers, right? See here, so many number of layers, the values becomes very small because of our activation functions, or because of our sum of product and all those things. So if it becomes very small, then the circuit will not build properly. Means, as I explained in the beginning, we need to build a good circuits to learn the classes, right? So the values becomes very small and small, that there will be nothing to learn in the neural network. Even the error rate will be very high. So if you try to back propagate it, or if we try to give the feedback to the system, because the values are very small, the system will not learn properly. So to overcome this, Google came out with an architecture. They call it as an Inception Net. So we have plenty of variations of the Inception Net. So first, I am going to explain about the first variation, Inception Net. So in the Inception Net, they have two different blocks. One is the stem block. This is what the stem block, and the inception block or inception module. See, till this architecture like AlexNet, VGGNet or LemNet, they started working only on stacking of the convolution layers, and that too also sequential stacking of the layers. But the first time they came out with a different approach called as Inception, where instead of having a sequential, they came out with the parallel filters, where that can be combined and to get the multi levels of representation. So this is one of the module they came out. See, and also till then we were using like a 3x3, 7x7 or 5x5 in a sequential manner. So now if you see here, they started with convolution 1x1 and also with the different kernels. In the same module, we have a different kernels like 5x5 and 3x3. So when you try to see this one, if you want to just logically relate what happens, see what these 5x5, 3x3, 1x1 will give. So as you all know that we have studied in image processing, as the size of the filter increases or decreases, the number of data points which was used for convolution will increase or decrease. Based on that, the more abstraction level or less abstraction level will be generated. So when I use 5x5, probably I will be taking a more larger area to learn. And if I am taking a smaller, the smaller region, the minute informations will be considered. So here we are trying to study the larger region, and here we are trying to study the smaller region. So minute information will be generated or collected here to analyze. Here probably a little bit bigger region will be analyzed. And when we concatenate these things, right? So this is what the concatenation process. So all the responses will be concatenated so that it will try to give very good representation. So that is one of the important thing that Google has presented, or InceptionNet has given that one. Okay. Apart from that, even they came out with another type of layers which was not proposed in any of the previous things, called as auxiliary layers. So till now, if you see, it was just like a sequential, right? So they will try to have something called as auxiliary layers. So what are these auxiliary layers, and what are the importance of these auxiliary layers, we need to understand. See, it's the same as our human learning. So if there is a one course for a student, right? So if it is a one semester, what happens? He will be joining to that course, right? And he has to, if he want to pass that course, he has to write the exam and he has to get very good marks, right? So our intention is not only to have students to get a good marks, right? But he should be able to generalize. Means he should be able to solve the real-time problems. That's why what we will do, we will try to give the internals in between, right? So that you will try to understand, okay, what mistake I am doing, so what I need to take care, so that in the final I will be having a good result. The same thing they used in the intermediate. Means, so in between the entire pipeline of the our architecture, they try to introduce between small classifiers or auxiliary layers, where after certain period of time it will try to perform a small type of testing, and it will try to understand where I am currently. So based on that, it will try to give the feedback to the system. So, and it will try to learn, okay, I am doing some mistake, I should understand, and that will be trained, and it will continue like this. So once again, we have another auxiliary layer. So it will try to understand and it will try to give the feedback. So if we do this one, the algorithm will try to learn properly and the final output will be very good. So that was the beauty of this InceptionNet. So I hope you appreciate this one by the authors, whatever they have presented this one. And also, if you see, this was deeper than VGGNet. So if you see here, this has more deeper than VGGNet. And here you can see that instead of having 3 fully connected layer, they have only 2 fully connected layer, and they have some intermediate layers. Now, if I try to understand how many parameters were used and all those things, so whatever I have explained, so it is present here. Okay, so they had a 22 layer architecture. Means like in VGG 16 or VGG 19 or 11, we had a 11 layer architecture, right? So Inception V1 was a little bit bigger than that, that is 22 layer. But the number of parameters which it was supposed to learn was very much less than VGGNet. Like in VGGNet, we were supposed to learn about 138 million parameters, right? In case of AlexNet, it was about 6 million parameters. Now the InceptionNet, being more deeper than previous network, the number of parameters to learn was very less, 5 million. So why that 5 million? It is because of this tower architecture. See, whatever we have here, right? So because of this, the number of parameters to be learned was very less. Okay, that's why the Google Net or InceptionNet works faster compared to VGGNet or AlexNet, and also it tried to give better performance. So I hope you appreciate this one. So this is one thing. So like at the end of the each paper, I have given what is the novel and the publication list and everything. You can go through that one correct paper. So in 2015, they came out with another version called as V3. So these are the blocks. Like initially, they started with only one inception block, right? So this was almost the same. So they came out with a multiple inception A, B, C. Okay, and they also used reduction A, B to have the appropriate architecture. So probably like if you try to understand this one by yourself, that would be very good. So that was very good, and they were having a very good performance compared to the previous architecture. Okay, so that required inception is a success of with 24 million parameters. So this inception V3 increased the number of parameters. That one. So this is the same thing. We have inception V4 and other things. If you are interested, you can go through that one. So in the same year, like in 2014, Google came with inception network architecture. So in the same time, Microsoft came with another architecture called as ResNet. So the difference between ResNet and InceptionNet is, so InceptionNet, it tried to use the auxiliary layers, and also they came out with the parallel architectures, or call it as a parallel towers. But what was the difference in ResNet was, so in art they also studied the VGGNet, means both VGGNet, after VGGNet was published, Google and Microsoft, they were working on the VGGNet. So main problem with the VGGNet, as I explained, as it becomes deeper and more parameters, it was not able to learn the things properly, means because of the gradient problem, vanishing gradient problem. So this ResNet, or Google, Microsoft, they came with an architecture called as ResNet. So what is meant by ResNet means, Res means residual net. So it is also called as a skip net. Okay, so they use not a skip net, they use a concept called as skip connection. So how this skip connection works, let us try to understand. So it is same. The ResNet, it was a sequential. There was nothing like auxiliary layers or something. Okay, it was same like a sequential, but the difference was skip the connections. So what is this skip connection means? Let us assume this one. So let us try to understand this one. We give the input, it will try to learn. Probably at this point of time, right? Because of the depth increases, so we were losing our gradients. Means gradients were become very small. The values were becoming very small. So what they said, okay, if this is becoming small, why don't you take the features from previous certain nodes and give as an input to the next node? So we have the residual, means some output is here, plus we have the previous output. Combine these two things and try to give. So that the vanishing gradient problem will be solved. So that is what called as a skip connection. So skip some connection, try to give the data. So that is what they did. So they also came with different layers of architecture. So like ResNet 50 was one of the initial versions. So they used about 26 million parameters. So probably you can go through this article, which will be very good. See here, if you want to summarize this one, ResNet 50, like input, convolution, max pooling, then identity 16, means identity, this is the block. We have the identity block, like convolution, 3x3, convolution 1x1, and add. So from here we will get some output residual, and whatever we had the output from previous node, right? So that will be added to this residual, and that will be connected. So like this way, they will be having 16 connections. So that is what the skip connection. So we will be having very good. So that was the one of the very good layers. So this was the most deeper convolution layers. Like they had like even ResNet 152 layers and everything, and they showed that it is performing better than VGGNet and all those things. So both ResNet and InceptionNet came almost in the same period. So that these are the different architectures we have. So after this work, right? So even Google came with Inception V4 and all those things, with just changing their architectures or inception blocks and everything they have worked. Okay. So after that, even Microsoft and Google collaborated, and they came out with combinations of ResNet and InceptionNet. So that is what. So if you see here, so these are related to the inception blocks, right? So we have inception blocks, and they used the skip connections. So here you can see the skip connections here, right? That is what the beauty of the Inception v4, which is a combination of ResNet and Inception net, which gave very good accuracy. So like this way, even we have multiple architectures called as dense net, mobile net, and so on. So even recently people are coming out with their architectures. So when we say architecture for convolution neural networks, right? So we are going to design a different blocks combination so that to solve the problems. So this is what I wanted to explain to you as a existing convolution neural network architecture. So if you have any doubts in this, you can ask me before I move on to the programming. So what I wanted to show you people is how to implement this one. So because it is related to agriculture, so I have taken a data set, rice leaf data set from Kaggle, and I have tried to implement two things. One is VGGNet, another one is the ResNet, and the implementation is very small. I have used Google Colab. So if you have any questions related to the presentation, we can discuss. Okay. So okay, like assuming that no questions has been raised in the chat. So okay, so I will start this one. So if you want to implement this one, right? So we have to use deep learning packages or platforms to implement this one. We have different kinds. One of them is TensorFlow, another one is PyTorch, another one is Cafe. Like this way, we have multiple things, Theano, and so on. So mostly or widely used one is nowadays is PyTorch or TensorFlow. So I am going to show you a demo on TensorFlow. Even the code has been shared with the organizers. You can take those codes. So if I want to implement this one, so normally we need to install this one. So I assuming like should I explain like how to open a Google Colab and all those things, or should I continue with the explanation about the programming? Okay. So I assume that you know how to open a Google Colab and all those things. It's very very simple. You can directly open your Gmail account. Once if you log into your Gmail account, you can type Colab, and if you click on that, it will open. And if you click on File and New Jupyter Notebook, it will open. So here almost we can write all type of program. So I have used TensorFlow GPU 2.3.0. So to install that one, we need to use this one, pip install TensorFlow GPU. So once you click on this one, like we have to enter these values, sorry, the statements, the commands. So it will try to install all the GPUs. Okay. So this TensorFlow requires it will be downloaded in the real time and in the system which has been given to you or allocated by the Google Colab. So it will be installing the GPU versions and all those things. This will take around some 1 to 2 minutes. So once these installations has been completed, right? So we can just check whether the which version of TensorFlow has been installed and all those things. So that is what. So because I already have installed, it is just checking. So once it is installed, we are going to import the necessary packages from TensorFlow. Because we are using this VGG16 as this one. In Keras, we have in TensorFlow Keras, we have a this one VGG16 model. We call it as a pre-trained model. So we are going to import that pre-trained model. So for each architecture, we need to pre-process the input. So for that, we have For that, we have this one, pre-processing the input. So if you are using Inception net, you need to use Inception. If you are using the RESTnet, you need to use appropriate RESTnet pre-process input. So this one is for image data generator, means whatever the data set we upload. So for that data set has to be converted into a suitable format to load it into TensorFlow and processing. So for that we use image data generator, and to load the images we use load image. Like somebody use OpenCV, if you want you can use OpenCV, or else using the TensorFlow Keras load image itself you can load. And normally ours will be a sequential, and NumPy and Globe, all these things, basic things will be used. And the data set I have uploaded to my G drive. So my Google Drive has to be mounted here. So to mount that one, this is the command. So I will try to just run TensorFlow and try to see whether it has imported these things. Okay, it has completed, and TensorFlow 2.30. So necessary packages has been installed, and I am trying to mount my Google Drive because my data set has been copied to Google Drive. From there, I am trying to access for learning. So it will ask for permissions to mount your Google Drive to collab. So you have to allow those things. So once you allow the Google Drive, it will be mounted. So now it got mounted. Now, if you click on this files or folder, you can see that my Google Drive has been mounted here. So if I go to my Google Drive, in my Google Drive, my drive, so I have created like a rice leaf data set. So in that rice leaf data set folder, I have two folders called as a train folder and test folder. So it's a 3-class problem, like the leaf diseases are like bacterial leaf blight, brown spot, and leaf smut. So same way the test. So you can have 3 folders. So for just for sake of implementation, I have taken a train test. So we should have train, validation, and test, as I explained in the beginning. We should have. So now it is mounted. Now we need to add this path for that one. So that is what adding the path. So here we have the train path and a validation path. So if you want to know what is the path, like how we get this path, just go to that folder. So click on train, we have an end of 3 dots, right? So if you click on here, it will give the path. So you just click on copy path and give the copy it here. So that is what it will copy. So we have just allocated. So next one is VGG16. So it's called as a transfer learning, or we are trying to load the model given by the TensorFlow. So here we have already imported that VGG16 here, right? So VGG16 we can import, and we have given what is the size. We are also loading the weights from the image net. So we are trying to load that one, the weights given by the pre-trained model, and we are trying to run it. So these are the things just to know like how many folders are there. So as we know that it's a 3-class problem, 3 folders are there. We'll try to do the flattening of this one layers and try to do this one. So just for sake of completion, I am running these things, the model, and you can see the model summary. So this is the summary of our model, like we understood, right? It starts with the input layer with the 224 by 224 and 3. And because this is a VGG16, it will be having 13 layers. And at last, it should have the these things. So this is what the parameters, the summary. So we can just run this one. So model compilation, and then data generator. So the data will be generated, required data generation has to be done here. So we are giving all the necessity, like I mentioned about the data augmentation also, right? So this is what this is pre-processing. We are trying to rescale the image, means the cell values, image values, intensity values will be divided by 255, so that it will be normalized between 0 to 1. Okay, and also we are telling that to do the augmentation, you use three types of geometrical transformation: shearing range, zoom range, and horizontal flip, and data will be generated. Okay. So data generation, create the training set and test set. So in the training set, we have 120 images, and in test set, we have 120 images belonging to 3 classes. So now data has been prepared. Now we need to train the model. So in machine learning or in deep learning, we call it as fit the model. So it says that you take the training set and validation set. So just for sake of completion, I have given 2 epochs. Okay. So 2 epochs. Epochs means what? Like whatever we had 120 images, all 120 images will be given 2 times for training. So while training, we have also given the details like steps per epoch, how much it should be, validation step, and all those things. It will try to perform training 2 epochs. So training is going on. So once the training is done, the model will be ready. So we can take that model and we can see what was the validation loss and what was the accuracy, everything, training loss and validation loss, and we can plot the graph. To plot that graph, this is the code. Like we can save the model, and once it is done, we can predict. So that prediction is present here. So you can see here what is the loss, means on the training data. So training data has been given as a data, and what was the loss at the current situation, and what is the current accuracy it is printing. So this is for VGG net. The code remains same except this statement. Like we are having 2 statement importing VGG 16, right? And also we are calling the model here. Yes, this statement. Now, if I want to change it to ResNet, it's a very straightforward. Just go there. Okay, the code remains, everything remains same. So instead of VGG 16, we are going to add ResNet 50. So if you go to Google, right? So TensorFlow 2.3.0 or 2.3 with VGG 16. So it will give you the complete details, like how to use and all those things. So I will just show you what are the architectures that VGG will present, means TensorFlow. Like you can see that starting from this mobile net. So these are the different architectures we have. So we have taken only VGG 16. Like you can see that 19 ResNet, ResNet RS, V2, ResNet, different architectures are there, so you can use it. So you have to import appropriate architectures, and you need to call that one. So remaining things will be almost the same. There will be no change. Only thing is these two. One is for appropriate architecture and pre-process. That's what I told. Like if you want to pre-process, if you want to work on a particular ResNet, so that pre-process input should be there. And this is what the summary of ResNet 152. You can see that how big the architecture is. So already I actually before starting this one, I trained this one for 10 epochs. And you can see that after 10 epochs, the validation accuracy, it was about loss was 0.93. Accuracy was 0.56, means 56.6%. So I have just given the 10 epochs. So if you give more epochs and if you add more data and do appropriate training, the accuracy will be increasing. The graph, you can see that training loss is getting increased and accuracy increases as the number of epochs increases. So now let us see what happened to our VGG net. Still it is being trained. So this is what simple, like you can take any of your data sets and try to run it. So why I took this example of deep learning is, so when I go through this paper, deep learning in agriculture, most of them were related to classification. So I thought that we will go for classification. However, if you want to use deep learning, you can think about unsupervised deep learning, or segmentation in the deep learning, or prediction, and all those things. So this is what I wanted to explain to you people. So still training is going on. So if you have any doubts, or this is what I planned for today's session. If you have any queries or anything, we have another 8 minutes. We can have a discussion on this. So even this is what the prediction, the class labels on unseen data. What is the data? So from this, you can calculate the confusion matrix. You can calculate vision, recall, F measure, area under the curve, and all those things that can be implemented. Someone has a question like explanation about the program. So what you want explanation means?
My side, actually, at the beginning of the session, you asked whether to continue with the program, or as you said, like, shall I explain the program or start from the basic architecture? So I was just pinged saying that just explain about the program. It was clear, sir. But then I have a query, sir. I hope you can hear. Hello?
Yes, ma'am. Yes, yeah, ma'am. I am able to hear you.
Yeah. Sir, like, how to decide the size of the hidden layers, sir, when we are designing the architecture?
See, the size of the hidden layer, there is no any specific rule or something. Normally, how we design or decide the number of hidden layers and also the nodes in the hidden layers. If I am just assume that your question is related to the neural network classifier, right? So normally we see how many number of features we have. Okay, so based on that features, we will try to identify like how many number of hidden layers should be there. So there are some set of thumb rules. Like one of the thumb rules, it says that if you have X number of samples, means input features, it says that at least you should have twice of number of neurons in the first set of hidden layers, and then you try to reduce it. Okay, that's a thumb rule. It varies from person to person. Like if you see that VGG net itself, right? If I just go back, I will try to share my screen. Just I will show you this one. So if we go to our first one, right? For the okay, see, first year they thought like I should have this one. Like if I take this one, probably this may be having around some 50 to 60 input neurons. So based on that, they will try to increase and they will try to reduce, and finally, you know that in the output layer it will be equal to this one. That's what, like same way here, because they had a huge number of layers, they kept means huge number of inputs because of the depth, so they kept it constant. So there is no specific rule or something. It depends on you and based on your experience, like how many hidden layers and what should be used.
Okay, sir, thank you. Sir, one more query I have. As you stated that we can use deep learning for segmentation as such. Can you just give some focus or some algorithms or architectures which are been designed for segmentation of data using deep learning?
There are many algorithms, like it depends on this one. So one of them is called as UNet. So in the deep learning, like if you search for this one, right, UNet architecture, but there are multiple architectures for image segmentation. So you can check, and almost it will be same mechanism. means the working mechanism, right? So it will be almost same. So probably if you go through this unit architecture, that's what they will try to do it. So they will take a input image and try to reduce or this one, and at finally we'll be having a vector. So from that they will try to reconstruct where the output will be the segmented map. So here also it will be just like a training. If I want to explain, normally in convolution, what we will do, we are going to use max pooling for reducing the size of the inputs.
Yeah,
Already.
to flatten.
So in reverse, they will try to regenerate the image. So that is called as upsampling or up pooling. Like that up convolution, they will try to do it. So this,
Okay.
if you see here, this is what they will try to do it. And finally, they will try to give the segmentation. This is one of the first kind of work for image segmentation. Apart from that, we have many algorithms like pixel level and all those things. Probably you can go through that one, ma'am.
Yeah, thank you, sir. Thank you so much.
Yes, ma'am.
Dear participant, have any queries or? So if you don't have any queries, we can summarize the session. So, shall I summarize the session, sir?
Yes, sir.
Madam Rekha, madam, please summarize the session, madam.
Okay, sir. Yeah. On behalf of the Atal FDP, I thank Manjunath sir for giving a informative session on deep learning architecture. It was very informative, and from the basic level, you have explained it very clearly, sir. And even the implementation of the architectures was very clear. Thank you so much. It will really benefit the researchers who are working under deep learning. Thank you, sir, for this informative session. Thank you.
Thank you, ma'am. And I thank the organizing committee for giving a chance to share my experience with you people. Probably like I should have asked in the beginning, like what was the expectation? I thought that I will start with the basics. That's why I went in detail about the basics. Sorry about that if I have repeated the same thing. Thank you all for your time, patience, listening. And if you have any doubts and any time, like I have given my email ID in the presentation file, which I have shared with the organizing committee, you can send me a mail related to this topic.
Thank you, sir.
Yeah. Thank you, ma'am.
Madam.
Thank you, sir. Thank you.
Sir, thank you very much, sir. You are accepting request. And our side, please accept our token of appreciation, sir.
Thank you, sir. No problems.
Thank you very much, sir.
Thank you. Thank you.
Okay, thank you, dear participants. So we are going to close the session. So we'll meet you tomorrow. So have a good night. Thank you, sir, once again, Manjunath, sir.
Yeah. Thank you, sir. Thank you, ma'am. Thank you.